Howdy, welcome to Severe Weather Europe. A substantial stratospheric cooling event is now being observed over the southern hemisphere following a massive injection of water vapor. There has been snowfall in South Africa and stuff like this a week ago, so let's dive into that. Most of you probably already know what's about. The strong and cold anomalies are being detected in the stratosphere over southern hemisphere. The anomalous cooling results from the water vapor coming from the January Honga Tonga eruption. Cooling on this scale has not been seen in modern satellite records, so this is a significant event. We will look at what is happening with temperatures in the southern stratosphere, how it all actually happened, and how it might impact our side of the planet in the upcoming winter 22-23. From the ground to the stratosphere. All of the clouds and our weather are found in the lowest layer of the atmosphere, called the troposphere. It reaches up to around 8 kilometers altitude over the polar regions and up to 14 to 16 over the tropics. Above it, there is a much deeper layer called the stratosphere. This layer is around 30 kilometers thick and very dry. There is where the ozone layer is found. You can see the layers of the atmosphere in the image below, with the troposphere on the bottom and the stratosphere with the ozone layer above it. So even the highest mountain, Mount Everest, is down here, and it goes still up. But we have to also notice this ends at 120 kilometers in height, which is here. That's a different way to show the atmosphere, since you will notice it continues still upwards, and it's still continuing upwards. Thermosphere and the magnetosphere and such. And here we can see that it's gonna be really hot every now and then. Hotter, like so aurora borealis and stuff. But let's go back to the article. This was a little piece about the thermosphere. So I just try to show you that it depends always on what kind of chart you're looking at, because it puts things into perspective. But anyway, these layers are important because while our weather is in the lowest part of the atmosphere, it can be heavily modified by the impacts from above. Especially the stratosphere is known for its effects and changes regarding the polar vortex, hence the Birkeland Current, which connects us to the rest of the universe. Every year as we head into autumn, the North Pole starts to cool down, but the atmosphere further south is still relatively warm as it continues to receive energy from the sun, while the polar regions receive much less over time. You can see the winter solstice below, as the polar regions receive little to zero solar energy. Yeah, I have been talking yesterday about the equinox. As the temperature drops over the polar region, so does the pressure. In the stratosphere, the process is the same. As the temperature drops over the pole and the temperature difference towards the south increases, a lower pressure cyclonic circulation starts to develop across the polar stratosphere. The image below shows a typical example of the polar vortex at around 30 kilometers altitude, 10 millibar level in the middle stratosphere during the winter. That's the northern part. It is basically like a very large cyclone, covering the whole north, down to the mid-latitudes. So it's strongly present at all levels. So it is strongly present at all levels, from the ground up, but in different shapes. But in the next image we have the polar vortex at a much lower latitude, around 5 kilometers. It reveals the true shape and size of the polar vortex closer to the ground. The closer to the ground we get, the more deformed the polar vortex gets because of the growing influence of the terrain and the many weather fronts and systems. Yeah, we could find probably better pictures about the polar vortex. We have to expect this kind of diachotron instabilities. And those instabilities, there are oscillations which are coupled to surface conductivity anomalies and ground charges and geological features within the ground. Might it be then geothermal or magma or metal content in the rocks and these kind of things. And since the mountains are made electrically too, and charge accumulates on peaks, the mountain ranges, valleys, and all these, they influence everything quite much. We are typically focusing more on the stratospheric polar vortex during the winter, as it plays a very important role in weather development throughout the season. It is known for its strong influence down from the stratosphere. But while we are more concerned with the stratosphere in the polar vortex of the northern hemisphere, a major cooling event is now unfolding over the southern hemisphere. So, it might be very interesting to see how the news picks this up, since everybody is running and shouting and yelling about climate change. It's getting so hot, there's no water and heat waves and all this kind of stuff. Europe, America, North America, China, which are all on the northern hemisphere. And the opposite is happening now in the southern hemisphere. Everything gets very cool. And we are in fall here in the northern hemisphere, which means they are going into spring in the southern hemisphere. We are now harvesting what's left, half of it, 30% of what should be harvested in order to feed all the people in the northern hemisphere. And in the south, they are supposed to put the seeds out in the fields. And it's getting cold. So it's getting simultaneously cold in the northern hemisphere because we are going into fall. And in the southern hemisphere because there is water in the atmosphere. And I've been talking about mountain water. Yeah, Honga Tonga was an underwater volcano erupting. Yes. But if you would take the bigger picture from it may be a quite big mountain if you would take out the water of the ocean. Honga Tonga, after all. Even though the elevation above sea level wasn't that much, now it's even less. So there was quite much water coming out there. Like to some degree also ocean water, but I guess also from the ground, beneath the ocean. But anyway, let's read this. I haven't read it yet. We began with the polar vortex in the stratosphere because that is where the main part of our story is currently unfolding. Strong volcanic eruptions can send different gases and materials directly into the atmosphere, depending on the type of particles and their amount. That can result in different regional and global atmospheric effects. Boom. The submarine Tonga volcano in the South Pacific erupted violently on 15 January 2022. Tonga produced a massive volcanic plume that briefly reached 58 kilometers, touching the mesosphere. Below, we have infrared satellite imagery of the eruption. We can see the warmer green-yellow cloud in the stratosphere and the colder black-white cloud in the troposphere. Very impressive. The eruption injected volcanic gases, sulfur, into the atmosphere and a large amount of water in the form of water vapor. The water volume in the plume was very high because the volcano is submarine below the water level, erupting out of the ocean. The video below shows the massive eruption sending water and volcanic particles into the stratosphere. This eruption was strong enough to send shockwaves around the entire planet several times over. Eruption reaches the stratosphere. Click play. Commercial about electricity. So, we are probably familiar with sulfur having a global cooling effect if ejected into the stratosphere in high amounts. One well-known example is the 1991 eruption of Pinatubo, which ejected a large amount of sulfur into the stratosphere, cooling the Earth's temperatures for the following few years, seen below. Like sulfur, water vapor has a cooling effect, but not at the surface. Instead, it actually cools the stratosphere because it reflects the incoming solar radiation. It also prevents the heat from escaping, thus actually warming the surface. So how much water is ejected into the atmosphere? Based on observations and measurements, the normal amount of water in the stratosphere is around 1,560 teragrams. Following the eruption of Tonga, the total amount of water increased to over 1,700 teragrams, which is a 10% increase in total stratospheric water vapor content. This is a large amount coming from just one event. Looking at the vertical analysis, we can see the injected water vapor in the image below. The water vapor was injected into the upper stratosphere, but the main concentration is between 20 and 30 kilometers. Below we have the NASA analysis of the water vapor anomaly at around 26 megapascal? MB? Megapascal. I don't know. Pressure level. Again, you can see the significant increase following the eruption spreading across the south and north hemisphere. And I have to show you windy. I made videos about this already many times. So here we are, it's still loading. Let's zoom out as far as we can. Because, for example, there might be other places as well, but I have been talking since months about this. There seems to be some connection being established from the equator straight into Central Europe. From the equator. So this is one point or one place where these two hemispheres might start to mix up. And it will affect many people because Europe is densely populated. So is the rest of the Northern Hemisphere. We produce a zonal mean plot for MLSR data provided by NASA. It shows the water vapor content in the lower to mid-stratosphere. You can see the water vapor cloud reaching deep into the southern hemisphere and also reaching into the northern hemisphere. So what? right is... How to read that? Where is north? On the left. Or is it on the right? Latitude north. I don't know. So the main takeaway is that a large water vapor cloud circles the globe in the stratosphere. As you will find out, it has a strong cooling effect and is likely to impact the global weather in some way over the coming months or years. And the sun is ramping up in activity, so does Earth. So there might be another Honga Tonga eruption kind like event coming. It has been somewhat quiet again, seismically spoken in recent 2 weeks or something. No bigger quakes, like many shallow and many quakes in the Alps and in Central Europe region, which are very interesting. But nothing big anywhere. So it might build up still before it releases its energy. Stratospheric cooling. As mentioned, water vapor is very potent at cooling the stratosphere. It deflects the incoming solar radiation, keeping the temperatures low. We will track these changes using the reanalysis data from the NOAA Physical Science Laboratory. Looking first at May 2022, we can see the mid-stratosphere temperature anomaly below. There was cooling already observed in the southern hemisphere. The strongest belt of cold anomalies was around the 30th south latitude. Australia, South Africa, where we had the snowstorm. By July, the cooling effect was stronger, and below we can see the cold anomalies moved further towards the South Pole, now maximizing in the mid-latitudes. The anomalies in July were substantial, reaching more than 10 degrees below normal. 10 degrees below normal. How much tax you would have to pay to get this? The image below was made by Simon H. Lee and also shows the July 22 mid-stratosphere temperature anomaly. The cross markings in the southern hemisphere marked a record minimal temperature which span in the belt around the whole southern hemisphere. That's one time around. And I think it's very interesting to see. I don't know what to make out of these, but there are these structures on the northern side which reach up north, but there are none on the southern side. And here I think we see the South American magnetic anomaly. But anyway, the NOAA mid-stratosphere temperature graph actually shows this unusual cooling. It is marked on the image below, reaching below the previous minimal temperatures in the past 40-year records. Yeah, I tell it again. We don't have more than 40 years to compare on this chart now. Keep this in mind. That's one very tiny part of temperature differences over a bigger scale. We are talking about 300,000 years, 500,000 years, and we are somewhere here. So how big is this compared to the bigger picture? 40 years. That's not even 40 years. This should be the picture below. And it is marked in the image below. That's the average of 40 years. Okay, I get it. Yeah, we are cooling. So, if you watch at that, it goes up and then it goes down. It goes up and then it goes down. It goes almost as rapidly down as it goes up. And now we went up. So what do you expect It can still go up a bit more, but since we had Tonga and there might be others following, and Tonga's already cooling, so we might going down. We might are going down. It's a repetitive pattern. It spans over quite a distance of time. But anyway, not only temperature as shown in the image below, but the pressure is also lower. You can see a belt of low pressure anomalies in the same region as the cooling anomalies. This is an overall significant change, anomaly for the southern stratosphere. This is an overall significant change for the whole southern stratosphere. Since we are all in this together, it will touch us all. There is actually something marked also between America and Europe. Looking at the vertical analysis, you can see the cold anomalies reaching all the way from the lower to the middle stratosphere. The strongest anomalies are confined between 30 to 60 degrees south latitude. Yeah, I have to continue a bit, because I don't know how long this still is. Looking at the same plot for pressure anomalies, you can also see the lower than normal pressure anomaly occurring with this cooling event in the vertical. It stands out globally as the southern hemisphere is in the winter season. And finally, the latest August analysis shows even stronger cooling. The cold anomalies are expanding further towards the South Pole, starting to influence the polar vortex dynamics more directly. Remember, we are going into fall, so they should go into spring, hence summer, hence it should get warmer, but it seems to get colder. The whole southern hemisphere. Latest analysis and forecast. The latest analysis shows the cooling anomalies connecting all the way into the polar regions. This makes most of the south stratosphere colder than normal. This is a somewhat expected result after such a strong injection of water vapor directly into the stratosphere. I just realized something. You can also see that on the latest vertical analysis, most of the southern stratosphere is colder than normal from the lower parts all the way into the mid and higher stratosphere. Man. Going into September, the cold anomalies will continue over the southern stratosphere as the polar vortex starts to weaken and the seasonal heating returns. Okay. It will be interesting to monitor the progress and the effects of the remaining water vapor. Looking at the vertical anomalies for the same September forecast, we can see stable cold anomalies. Stable cold anomalies. Stable in what? How stable? This is likely to continue for several weeks as the cooling effect will persist as long as the water vapor concentration is high enough. Seasonal weather influence, of course. We all want to know how this will impact the global weather, especially if at all, in the upcoming winter 22-23. For this purpose, we have produced a simple July-September temperature index covering the stratosphere over the southern hemisphere's mid-latitudes. You can see it below, having several warm and cold years. Yes, again, 40 years, which isn't telling us the whole story. What we can do is compare this changing index to year with changing temperature and pressure pattern story. But you know what? I have to tell you now the thing I was thinking about or came to my mind while reading this. So now I make it easy. I have been talking about continuous ash plumes are like antennas for more energy. Volcanic ash clouds being antennas doesn't seem so crazy to me anymore. I have also in my paper this picture about Birkeland Currents, Peterson and Hall currents, which are connecting, which are the magnetic north and south poles of Earth. And now we go to Google, null school, wind, and we go at the highest we can get. North Pole, nothing really going on. South Pole, very active still. So if there's this Honga Tonga stuff spinning in this, it might work like an antenna for more energy on a much bigger scale than I thought initially. Now, when I was reading this article and thinking about this, let me draw you the Birkeland Currents. And there is the sun. So if the sun is putting out more energy, Earth will emit more energy as well. There are many volcanoes in the southern hemisphere, Antarctica and such. So it might be very interesting how the Honga Tonga eruption makes it different for the energy to flow between Earth and Sun. It could induce very much more energy just because of the Honga Tonga eruption. It might get very interesting, but I think I'll leave it here. That's a very long video. But it could be continued for as long as we have internet. Anyway, I leave it here. Thanks.